Hey guys, what's up? Welcome back here. I'm here with another, lecture, and that's again from Biomolecule. I've already done in Hindi, and this is going to be, for those who need in English, right? So what this time is, this time it's about structure and the naming of the glucose, right? And these are the two main things I'll be describing. This is again going to be a short lecture, but very useful for all your exam you might be having this year. So what this is, I've already taken the topic here. This is glucose, and a glucose has basically some structure because it is an optical isomer. So it has two isomers. One is called dextrorotatory, another is called levorotatory. So things things from today's lecture are going to be around all that. Let's take you through the topic and explain you what I'm talking about. The first thing I wish to tell you that a glucose molecule has 6 carbon in chain, right? We are doing the open structure. So this is the 6 carbon. The first carbon has aldehyde group. Either you can place it CHO like this, or you can also place it like you can place it this way. So the first one is here, and the last one is having a CH2OH. Now, the very important thing about this particular structure is that if you are doing dextrorotatory glucose, this is what very important is. If you are talking about dextrorotatory glucose, then this is the structure. So because it is dextrorotatory, what is important here, you need to be concentrating about that the very second carbon, after the aldehyde carbon, you have OH group on the right side. What that means, you have an hydrogen on the left side, and the next carbon you have OH on the left side, while this one is having hydrogen on the right side. But on the remaining carbon, this fourth one and fifth one, you have your hydroxide both on the right hand side. So this is the structure. What that means, hydrogen is occupied on the left hand side. So this is the structure of dextrorotatory glucose. So let me write again. I have written over already there. So this is your plus glucose, and this represents to dextrorotatory. What I'm going to do, I'm placing a mirror here. I'm placing a mirror, and suppose this dotted line represents to a mirror. And if you are observing the mirror image of this dextrorotatory glucose, what you will be observing? You will be observing something like this one. You have your C. Now the O will be this time right over here. Hydrogen will be right over here. And just place the 6 carbon first. 1, 2, 3, 4, 5, and last one you have 6. So what is important here? Now this will be, the OH will be now on the left hand side. So place the OH on the left hand side and hydrogen on the right hand side. Similarly, now the OH will be on the right hand side and hydrogen will be on left hand side. Last one is your CH2OH. Last one is your CH2OH. You don't have to be worried about the position of OH on the last carbon, because this is not chiral. Let me write you. This is a chiral carbon. This is a chiral carbon. While these 4, but let me finish it first. So you have your OH here, you have again OH here, and hydrogens are on the other side. So like I was saying, when we see that these 4 carbons, these are actually chiral carbon. This is carbon, again a chiral, this is again a chiral, and this is again a chiral. So let me write this. This is a, these 4 represent to the chiral carbon. So what I'm doing, I'm writing over here chiral. So these 4, carbon atoms are chiral here. These 4 atoms are chiral here. And this one is, achiral. This one is achiral carbon, and there is no need to consider because this has a hybridization of sp2, so we are not concerned about. Similarly, these 4 carbons, are chiral right here also. So this is also your chiral. This is again your chiral carbon. This is again your chiral carbon, and this is again your chiral carbon. And similarly, this will be a achiral, which I am not writing again. But let me give you the reason why these 4 are chiral. What is a chiral carbon? A chiral carbon is a carbon where all the 4 substituents are different. Well, all the 4 substituents are different. Let's see that. At this carbon, you have aldehyde up here, hydrogen on the right side, OH on the left side, and this huge remaining part on the downway. So this is going to be a chiral. Similarly, if you take a look right here, up you have over, all these are here, up here, OH on the right, H on the left, and this again is a very huge molecule here. Similarly, the third and fourth, they are also chiral. So there are 4 chiral carbon, and we have to pay attention on the chiral carbon only to find out which one is dextro and which one is levo. Now pay attention, in the dextro, there are 3 OH on the right side, 3 OH on the right side, right? So should I write? Let me, 3 carbon, 3 OH in fact, 3 OH are on the right side, in dextrorotatory, but 3 OH are on the levorotatory, but only on the chiral carbon, the chiral carbon. What that means is that you have to be concerned about only the OH that is present on the chiral carbon. Right? Now, these are the structure. So this is your, this is your second isomer, and what this is called? This is called levorotatory, glucose. Levorotatory glucose. I hope I made you understand, because this is something. In the levorotatory, 3 OH will be on the left hand side, but in the dextrorotatory, 3 OH will be on the right hand side. But we have to pay attention to only those OH which are on the chiral carbon, not any other carbon we are concerned about. Now there is something else I need to explain you. There is a compound which is called dextrorotatory glyceraldehyde. And there is another one which is called levorotatory glyceraldehyde. Okay, now I am placing a mirror here because I will be looking for that. Okay, what this glyceraldehyde is, this is something very important, because this particular compound has something very important related to the glucose molecule. A glyceraldehyde is having CHO, and you have another carbon where OH is on the right hand side and hydrogen is on the left hand side, while there is CH2OH. Now this is called dextrorotatory glyceraldehyde. Why? Because this carbon is chiral. This carbon is again chiral, and it has OH on the right side. This OH is on the right side. So what that means, in the levorotatory, this is going to be CHO, where the next carbon will be having OH on the left hand side, and last one we have nothing to worry about, because this is not even chiral. So this levorotatory has OH on the left hand side on the second carbon from the bottom. This is the second carbon from the bottom. So this is called levorotatory glyceraldehyde, and this is called dextrorotatory glyceraldehyde. Now get back to the very important part here. All the compounds with 6 or more carbon which have structural similarity with the dextrorotatory glyceraldehyde, they are assigned a capital D before their name. So because this compound and this one had something to similar, the second carbon OH on the right side, the second carbon OH on the right side. So because of the glucose had something to do with this molecule, this glucose is also assigned D before its name. And this molecule is similar to the levorotatory glucose, so this has a L before its name, right? So this is your second structure of glucose, and this is your first structure of glucose. Now the D and L actually represent to the structural correlation with the glyceraldehyde. D stand for dextrorotatory glyceraldehyde configuration, L stand for levorotatory glyceraldehyde configuration. So in case you find, that's D and L, just take it like this is something coming from the structural correlation from glyceraldehyde, because it also has 2 optical isomers like I have already drawn right here. So these are some of the very important thing I wanted to make you go, related to glucose. I would say, I have to wind this right here, study them and let me know how good or bad this was. Thanks for watching, take care, and don't forget to come back for the next lecture.